So far in our course we've looked at functions like straight line functions, y equals mx plus c. We've looked at quadratics of the form y equals ax squared plus bx plus c, and also in vertex form. And we've also looked at various polynomial functions. In this short section we're going to look at an extension of that. We're going to look at exponential functions. Now, exponential functions differ from polynomial functions in that the x value is a power, an exponent, if you like. If you remember, the polynomial functions, it was always x squared or x cubed or x to the power of 4. Here, the power, the x, is at the top. It's this exponent. Right? So we have exponential functions. And they could be 2 to the power of x, they could be a half to the power of x, they could be 4 to the power of x, 3 to the power of x, anything. Anything but not 1 to the power of x or 0 to the power of x. Now, if we look at this first function, y equals 2 to the power of x, what we've got is some just random values of x, more or less, at -2 up to 3, and we've calculated to get for example, the 8 here, we've done 2 to the power of 3. 2 to the power of 3 gives us 8. 2 to the power of 2 gives us 4. 2 to the power of 1 gives us 2. 2 to the power of 0 is 1. Remember, anything to the power of 0 gives you 1. 2 to the negative 1, that's 1 over 2. 2 to the negative 2, that's 1 over 2 squared, so it's 1 over 4. And when you graph these points, 1, 2, 2, 4, 3, 8, 1, 2, 2, 4, 3, 8, we get this kind of smooth curve here. And it has what we call an asymptote. It gets closer and closer to the x-axis, but never quite gets down to 0. It gets lower and lower, smaller and smaller, but doesn't quite get there. And there are other exponential functions too. Here we've got these exponential functions. We've got 4 to the power of x. You could graph that in exactly the same way. You'll notice that when x is equal to 1, y is equal to 4 in this graph here. When we had y equals 3 to the power of x, when x is equal to 1, we have y equals 3 in this example. And it's the same for all those things. This 1 to the power of x thing here is not a very exciting one, because 1 to the power of anything just gives you 1. So it's just the same as the line y equals 1. And the only other kind of thing of interest here is the function y equals a half to the power of x. Notice it's this function here. It's the reflection of y equals 2 to the power of x in the y-axis. If you reflect y equals 2 to the power of x over the y-axis, you'll get this function here. And that's because a half to the power of x can be written as 2 to the power of minus x. And you'll remember from our work that we did on transformations, if you replace x with minus x, it has the effect of reflecting the function in the y-axis. So, generally you can have more or less any number down here, the b in this example. That b is called the base. And it can be any number. Generally we don't use 1 and we don't use 0. But it could be any sort of fraction, and it could be any generally positive number also. Gives us nicer functions. So we say that b isn't equal to 1 and b is bigger than 0. It's positive. Now we come across exponential functions whenever we see a kind of phenomenon known as exponential growth and sometimes exponential decay. Now, exponential growth takes place whenever you're kind of over, for example, at some time period, you're doubling something or tripling something or multiplying something by 4. What happens is that for every value, for every unit of x, the function gets multiplied by the same number. So if you're going from here to here, we're going to cross by 1, so we're multiplying by a certain value to go from here up to here. And if we're going from here across to here, again we're increasing the x by 1, so we're having to multiply the y value by the same amount to get up here as we did to go from here to here. Another way of writing that would be that b3 divided by b2 would be the same as b2 divided by b. And every time you go across 1, you're multiplying by the same amount. Okay, so the function increases by a factor of b every time you increase x by 1. And exponential decay works in exactly the same way, except you're dividing by b. Every time you go across 1, you're dividing by the same number b. Now, looking at example 1, if you wanted to graph this thing here, this fairly simple exponential functions, just take some simple values of x. Usually we do something like -2 up to 4 or -2 up to 3, and just plug in x equals -2 into this. So 2 to the power of -2 is 1 over 2 squared, that's 1 over 4. So you have 1 over 4 times 3 gives you 3/4. Do the same thing here. 2 to the power of -1 is a half. A half times 3 gives you 3/2. 2 to the power of 0 is 1. 1 times 3 is 3. 2 to the power of 1 is 2. 2 times 3 is 6. 2 to the power of 2 is 4. Times 3 is 12. 2 cubed is 8. Times 3 is 24. 2 cubed is 16. Times 3 is 48. Now you'll notice here that every time we increase x by 1, for example, if you go from here to here, we're multiplying the y value by 2. Same thing happens from when you go from here to here. The y value gets multiplied by 2. 6 times 2 gives you 12. When we go from 2 to 3, 12 gets multiplied by 2 to get 24. 24 times 2 gives you 48. So here we would say that the growth factor is 2.